introducing. So welcome everyone to Vassili's seminar as part of the AFMS series today. So Vassili's happy for you to ask any questions that you have throughout his talk. So if you do have any questions, just put a little bit of text into the chat box, or use the hand raising icon and feel free to ask Vassili your question. So Vassili's done a lot of interesting work since as both a postdoc at CSIRO and at Monash, and then again at CSIRO as a staff member, I suppose, on parameterization of subgrid processes at both planetary scales and also at sort of industrial type boundary layer scales. So today he's going to be talking about the use of Kalman filters to parameterize temperature fluxes in a coupled atmosphere ocean model. So thank you, Vassili.
Thanks,
also, sorry, I should also say Vassili's webcam doesn't appear to be working. So if you go online and Google a picture of Vassili, maybe pop it up there or something on the screen.
Okay, great. Thanks, mate. Cheers. All right, so we'll just get started. Okay, yeah, so firstly, just like to acknowledge CSIRO for funding my position, specifically in the Decadal Climate Forecasting Project, and also the NCI for providing the computational resources to do the work via the NCMS scheme. Also all the efforts of my co-authors, and also Dr. Pavel Sakov for his many discussions during the development of this project. Okay, so what's the problem that we're trying to address? The problem is model biases limiting predictability in general circulation models. So for those of you that aren't familiar with what a GCM is, it's essentially a numerical representation of the Earth, subject to solar radiation, CO2 forcing and other forcings, land use changes, etc. The problem is that the Earth system is multi-scale and highly nonlinear, which means unresolved processes must be parameterized. And many of these parameters are known with little precision, and this contributes to model bias and hence limits predictability. So just to kind of maybe put in context how multi-scale the Earth is, we have everything ranging from millimeter scale atmospheric turbulence all the way up to planetary waves, which are hundreds of thousands of kilometers and everything in between. And associated time scales ranging from seconds to tens of thousands of years. And it may seem maybe obvious, but small things of small spatial scale are fast. And as you go up in the spatial range, things get slower and slower, or longer and longer time scales. So the only things that are predictable over multi-year decadal timescales, which is what we're interested in, are the very large things, like the El Nino and La Nina cycle, for example, which is kind of what we'll be targeting. As you also go up in timescale to longer and longer timescales, what's important in a forecast system also changes. So for weather prediction, it might sound odd, but weather prediction is all about trying to know what the weather is right now. We don't know what the weather is right now because we don't have a temperature sensor everywhere. And this uncertainty in your starting point essentially dominates your error growth. So it's dominated by your initial condition error. So it's an initial value problem. And likewise for seasonal prediction. Climate projections are at the other end of the spectrum. When you're running simulations out for hundreds of years and you're interested in the statistical properties of the climate 100 years from now, the specifics of the initial conditions are not important. It's all about how much CO2 you're putting into the atmosphere year on year for the next 100 years. And that's subject to economic development and technologies, which we obviously don't know. So decadal prediction is kind of in this kind of weird no man's land where both initial value problems and boundary conditions are important. So initial conditions are important because we need to know what phase of the El Nino and La Nina cycle we're starting in, but also over a 10-year time scale, you can imagine uncertainty in CO2 emissions are going to affect the simulation. Okay, and to kind of complicate things even more, there are various classes of general circulation models. Atmospheric GCMs simulate the atmosphere with an ocean temperature boundary condition, and this typically produces realistic El Nino and La Nina dynamics by virtue of this boundary condition. Oceanic GCMs, which simulates the ocean forced by atmospheric winds, Again, this also produces realistic El Nino, La Nina dynamics. And then there's a more complicated couple GCMs where you have a dynamic atmosphere interacting with a dynamic ocean. Now you don't have that boundary condition at the air-sea interface, but the fluxes between the air-sea interface is parameterized. And this arguably introduces additional biases, or just the fact that you don't have a boundary condition there. It's a lot of kind of missing information, if you like. So how can we go about minimizing these biases? The typical approach, essentially do a sensitivity analysis. You run various simulations, each with manually tuned sets of parameters, and some determination is made on which set of parameters produces the most realistic results. Another potential solution is to calculate the parameters from subgrid statistics of high resolution truth simulations, such that the lower resolution versions match the statistics of the truth cases for all scales. And we've successfully done this for idealized quasi-geostrophic atmospheric flows, idealized quasi-geostrophic oceanic flows, and also turbulent channel flow. It's RETAO 950. But what happens if a truth case is unavailable or too computationally expensive to run? So that leads us onto the approach we're going to go through today, which is to exploit real-world observations to estimate both the model state and also the model parameters using the Ensemble transform Kalman filter. So in a way, you can think of the world being our truth case, albeit we can't observe the world at all times and space that we would like, nor can we observe it perfectly due to instrumental error. So just kind of give you a bit of an overview of what I'm going to go through. First of all, very high level equations of what we're going to go through, what we're solving in the coupled GCM. General overview of Kalman filtering in both the state and parameter estimation context. The specifics of the system that we're using to solve the problem, we call it the Climate Reanalysis and Forecast Ensemble System, or CAFE. And then demonstrate the sensitivity to the estimated parameter fields, and also the skill, if you like, of the general circulation model, subject to either estimating these parameters individually or simultaneously, and also the sensitivity to how often you do the simulation. Okay, so general circulation models are very complicated beasts. They're tens of thousands of pages of lines of code. So I've kind of done my best to strip it down to its bare bones of what's actually being done under the hood. So we essentially solve the Navier-Stokes equations on a sphere, all the standard things: conservation of mass, conservation of momentum, scalar transport for humidity in the atmosphere, scalar transport for salinity in the ocean, and also for biogeochemical concentrations in the ocean. So that's phytoplankton, zooplankton, dissolved inorganic carbon, a whole raft of other things. There are also equations of state for the atmosphere and in the ocean. And then the conservation of internal energy equation. So this is the only one that I've kind of explicitly spelled out here, because it's the parameters within this equation that we're going to be estimating. So here we've got the time derivative of the product of density and internal energy I. I've written this in volume integral form, and there's a reason for that. So that's given by the volume integral of the gradient of density, internal energy, and velocity, plus our conduction term. And then we've got heat sources due to phase changes, or latent heat, long wave radiation, short wave radiation. So short wave radiation is incoming short wave radiation from the sun, and long wave radiation is the black body radiation from the Earth. And then we've got our kind of pressure work term. So these first terms up to here, we can use a divergence theorem to turn them into a surface integral. And so again, these two are identical, but the reason I've written it in this form is that at the air-sea interface, the surface integrals need to match. So what I mean by that, the fluxes of heat due to conduction, transport, latent heat, long wave radiation, short wave radiation coming out of the ocean need to match those that are going into the atmosphere. And each of these terms are parameterized in their own unique ways. So after some initial testing in the full data simulation system, the parameters governing the shortwave flux exhibited the greatest influence. Parameters influencing the other fluxes were either found to be ineffective or produced numerical instabilities, which is an indicator of model form error. We can maybe talk about that later. So in terms of the shortwave radiation, if you can imagine shortwave radiation coming in from the sun, it gets to the top of the atmosphere. This radiation is then scattered and reflected and transmitted all the way through the atmosphere using quite a complicated energy balance model that I'm not going to get into today. Once it gets to the ocean surface, it's then either, part of it is reflected due to the ocean's albedo, given by this simple expression here. And then the remainder of that penetrates into the ocean, and the depth to which it penetrates is given by this other parameter, L shortwave. So these are the two parameters that we're going to be focusing on during the course of the talk. The albedo of the ocean and this shortwave penetration depth. You can kind of think of it as inversely proportional to opacity. The more opaque the ocean is, the less the radiation can penetrate. The less opaque the ocean is, the more the radiation can penetrate. And the opacity of the ocean is related to various things, chlorophyll concentrations, a whole bunch of other factors as well. So David, I might give people the opportunity to ask a question now, because this may be a logical place before I get into the Kalman filtering stuff.
Okay, does anyone have anything? I mean, I've got a question if no one else does.
Fire away if you're...
My question was, so in terms of the internal energy conservation, this is typically balanced by temperature fluxes and pressure gradients.
Yeah.
And typically numerically, they are not discrete, that balance isn't satisfied discretely.
Yeah.
I was wondering if this is something that I know this isn't about fluxes between the atmosphere and the ocean, it's internal to either the atmosphere or the ocean.
Yeah.
But I was wondering if that's a consideration.
Well, I guess it will become obvious when I kind of go through the Kalman filtering equations that the Kalman filter can't interpret the different sources of bias. So I've kind of gone through here and symbolically, I guess, illustrated the various sources of fluxes. And in doing these experiments, the shortwave flux was the only one that really had any influence on not just the fluxes, but every other state variable in the system.
Okay.
So when you're estimating these parameters, it's on the basis of it's matched to SST, sea surface temperature, sea ice concentrations, atmospheric quantities. They all contribute to estimating these parameters. So the value of these parameters isn't just about getting the fluxes right. It's about getting the system right in its entirety.
Gotcha.
So in doing so, you might not be addressing alone errors in the fluxes. You could be addressing errors in mixing and in all sorts of other things. Yeah. Which I'll kind of get to later on in the talk.
Sure. Tushar also has a question. Would you like to ask your question, Tushar?
Just a small question. So for the shortwave fraction, you mentioned about this being correlated with penetration. Sorry, I just lost it. Could you please explain again?
Yeah, sorry. Yeah, so this shortwave length scale, it essentially says how quickly, with depth, shortwave radiation goes to zero. So if you have a very large value of L, then that allows the shortwave radiation to penetrate to greater depths into the ocean. If you have a small L, then all of the heat is concentrated near the surface.
Oh, okay. Yeah, that clarifies. Thank you so much.
Yep. Okay, great. Thank you. So if there's no other question, I might continue. That's okay. Dave?
Yep. No, it looks like we're good.
Okay, great. So so that was kind of a logical place to stop. Now I'll kind of go through the Kalman filtering theory. So the Kalman filter was first developed in the 1960s. Data assimilation in general, be it Kalman filtering or not, modifies imperfect simulations of reality with a series of incomplete and possibly noisy measurements, we denote here by Y, ideally resulting in a better representation of the true system state. So the Kalman filter was developed for a linear system with Gaussian process noise W and observational noise V. So it's linear because we have a linear operator F acting on the previous value of the system state. And the observation is such that we're observing the system linearly as well, subject to noise. So the Kalman filter has two steps, an analysis step and a forecast step. During the analysis step, you're essentially minimizing the error of the analysis covariance matrix. Just think of it as a measurement of a measure of error between the observations of in the model. And your analyzed state, your superscript A here, is given by your forecast state, which is what your model would have done in the absence of any corrections, plus your Kalman gain multiplied by the difference between the real world observations and your model observed in the same way that you're observing the real world. So this H operator mimics what your sensor is doing. And this Kalman gain is given by your forecast error covariance matrix multiplied by your H linear operator multiplied by the inverse of the sum of what you can think of as model error and observational error. So the Kalman gain balances observational error against measurement error. So you can think of the two limiting cases where if you have zero observational error, then regardless of what the model tells you, you're going to snap all of your model states to the observations because you're 100% certain that your model has zero error. In the converse case where you have zero model error, regardless of what the observations are, you're going to ignore them because you're 100% confident that the model is the truth. In reality, neither of those two cases ever happen. So it's always, the Kalman gain kind of tells you how much you're going to nudge toward the observations without necessarily ever snapping exactly to them. So that's the analysis.
Sorry, Vassili.
Yeah.
There's a question from Mohammed Reza. He's just asking if you can use your mouse as a laser pointer. I don't know if that's...
Oh, yeah. Yep. Sorry, I was doing that, but with my finger, so which obviously wasn't working. All right. Yeah, I'll do that with my mouse. Yeah. Okay, great. So then there's the forecast step, which takes these analyzed states. So all of these analyzed states have essentially been corrected subject to the available observations. And then they're moved forward in time using your F operator. And likewise, you also propagate forward in time your error covariance matrix. Okay, so then the next major, I guess, development in this area was the extended Kalman filter, which was essentially applying all of the same mathematics, but to nonlinear systems instead of linear systems. But now, instead of optimally minimizing the error, we're suboptimally doing it because we can't guarantee optimality in these nonlinear systems. So you'll notice here we have this script F replacing our linear operator for F, and this script H replacing our linear operator for H. So the analysis update equation has changed slightly where we have our full nonlinear operator acting in here. Our Kalman gain equation has symbolically not changed, but now we're redefining H to be the tangent linear operator of our full nonlinear function. And likewise in the forecast step, the evolution of the state has not changed, but we have redefined F to be the tangent linear operator of our full nonlinear system. And when I'm referring to F, I'm talking about the general circulation model here. So this worked fine for weakly nonlinear systems, but when you get to strongly nonlinear systems, this tangent linear operator approximation is just not sufficient. And in many cases, it can send you in the wrong direction. So then the next major advance, and this is what we're using in our system, is the Ensemble Kalman filter of Evensen. So again, we're still applying it to a full nonlinear system where F here is our massive general circulation model. But now instead of relying on these linear operators to march the statistics forward, we're going to sample them. So now you'll notice a subscript E here, sorry. So here, this is an ensemble of different Earths. So in our system, we have 96, but we'll get into that later. But so for Earth E, the analyzed state of Earth E is given by the forecast state of Earth E plus the Kalman gain multiplied by the difference between the observations and the observed model. Kalman gain operator again, the Kalman gain operator is again not changed. The major difference here again is the forecast step. So instead of having instead of relying on the linear operators to evolve the expected state forward, we can evolve each of the individual Earths forward and then take statistics of the individual Earths. So we can get the expected state from the average Earth, and then we can get the error covariance by sampling all of the individual Earths. So this will become more clear on the following slide. I've got a little schematic that illustrates how this all works. Okay, so here I've only drawn 4 Earths for clarity, but in the system that I'll talk about next, we have 96 general circulation models all running at the same time. So at time t0, we have 4 distinct Earths here, each with different initial conditions. They're all marched forward in time, and since it's a nonlinear system, you have nonlinear error growth, so they all spread, they become more disparate with time. And then we get an observation. So this yellow dot is to represent not just one observation, but a raft of observations, satellite measurements, altimeters, Argo floats, whatever observations of the Earth system that you have. And then you use the Ensemble Kalman filter mathematics to make all of these Earths look a little bit more like the yellow Earth. So not only do you have the ensemble averaged Earth, which tells you the systematic similarities between all of the Earths, but you also have a whole PDF of Earths. That's kind of what this green blob here is supposed to represent. So you notice that the forecast ensemble has a wider spread or larger standard deviation than the analyzed ensemble. That's because all of the Earths are pushed to look a little bit more like the observations. So this process is repeated time and time again. So at the end of this analysis phase, at time t1, they're all evolved forward in time at time t2. Another observation comes in, you correct all the Earths, you evolve them forward, and so on and so forth. What we do is actually specifically called the ensemble transform Kalman filter, where the ensemble mean is updated just as I explained, but we do something a little bit different with the deviations from the mean, but we can get into those details at question time if people are interested. So what I've explained to date is ensemble Kalman filtering for state estimation. What this slide is I guess, the point of it is to demonstrate how we can use that same framework, but to also estimate the parameters. So the mathematics doesn't change. All we need to do is to redefine what the state is. So before we had this state vector representing only the states of the model. So temperature, velocity, pressure, salinity, specific humidity, or sea ice concentrations. But now we're redefining that with this superscript S. So they're the model states. And then following that, we have XF superscript psi, which represents the parameters. So this is the shortwave length scale and also the ocean albedo. We also analogously redefine the analyzed set of states. And we also need to redefine our linear operator for the observations, where HS is now how we're observing how the instruments observe the world. And this matrix of zeros is just saying that the satellite that measures ocean surface temperatures doesn't know anything about the ocean albedo in my model, which seems reasonable. So when you make these substitutions into the Kalman update equations, we get our analyzed state here for the states and the parameters is equal to our forecast states and our forecast parameters, plus the Kalman gain multiplied by the difference between the observations and the observed state. Where the Kalman gain is now here given by this error covariance matrix between the states, multiplied by the inverse of the sum of the error in the observations and the sum of the error in the model. So this top line is identical to what we saw before. The bottom line, and this is what's responsible for changing or estimating the parameters, is that this covariance matrix is the covariance between the ensemble of parameters and the ensemble of states. So that's kind of the important part. So maybe in words, to maybe give you a concrete example of how this works, if we have a particular observation of temperature at a given point in space, we can use that temperature observation to correct all of the different Earths at that one point in space. But if the model has spatial correlations in temperature, then we can use that one temperature measurement to not only correct temperature at that point in space, but also correct temperature at the surrounding points in space. And additionally, because the state vector is multivariate, it's not just temperature, it's velocity and sea ice and all the other things. If velocity, for example, is correlated with temperature, then you can use a temperature measurement to correct velocity through the model correlations. And to take it one step further, if my ensemble of ocean albedos is correlated with my ensemble of model temperatures, then I can use a temperature observation to correct not only temperature and velocity, but also albedo. There is one important choice though that we need to make when we're doing this. It's the choice of how often you do these updates. Because as you might imagine, the strength of these correlations really define how well you can estimate these parameters. So if there are no correlations, Kalman gain is 0, you're not making any intelligent changes to the system. So the shorter the forecast window, or if you're doing your update more often, the evolution of the system at the end of that forecast is more strongly correlated with the specifications of your original set of parameters. But if you run this model for longer, then you start to get more and more nonlinear interactions, and the correlation of your final set of states with your set of parameters becomes weaker and weaker. So in the context of having a well estimated Kalman gain, or a well sampled set of covariances, then shorter DA cycles or shorter forecast windows are desired. But on the flip side, this difference between the model and the observation and your model, this tells you how much you're going to essentially correct your states or your parameters. And for shorter and shorter window cycles, this gets smaller and smaller. So you have kind of conflicting requirements on this forecast window. Ideally, you'd want a large difference between your observations and your model, and that's going to essentially draw out the biases that you're trying to fix. And it's those things that are then multiplied by the Kalman gain. So that's kind of a long-winded way of saying I'm going to look at the sensitivity to a data simulation cycle length. So these are the specifics of the system that we're running. So the data simulation system itself has been recently published. It's an ensemble transform Kalman filter specifically designed for high-dimensional geophysical flows. There's 96 ensemble members. It's 10 to the 8 model states, and it requires about 10,000 CPUs to march all 100 or 96 ensemble members forward in time. We use all the observations that we're going to get our hands on, which include satellite and subsurface ocean observations. We use the Japanese reanalysis as a pseudo-atmospheric observation, satellite sea ice concentrations, and the model itself is from the Geophysical Fluid Dynamical Research Labs. It's a 2-degree atmosphere in terms of resolution, 2 degrees in latitude, 2.5 degrees in longitude, 24 vertical levels. The ocean is high resolution, 1 degree longitude, and finer resolution at certain latitudes with 50 vertical levels. And the sea ice is on the same grid as the ocean with 5 thickness categories. So Dave, I might stop there for questions again, because I'm going to kind of get into results. If anything was unclear about the Kalman filtering, I can maybe address any questions.
Does anyone have any questions for Vassili?
Well, I have a question, Dave.
Oh, sorry. Yep, Sean.
Vassili, I'm wondering, for the ensemble Kalman filter, is it literally just you're running a bunch of different independent simulations with different initial conditions, which then give you a different state at each time instant, and that becomes a different initial condition going to the next time instance? Am I interpreting this correctly?
That's exactly right. Yeah.
And so my question, I guess, is how do you initialize the very first initial conditions? So in other words, how do you get those 4 different Earths at the very beginning?
Yeah. So this might be a Well, realistically, you take it from a previous experiment. So
Okay.
The initialization of the very first set of Earths, we did using like kind of a statistical approach. So we ran one model for many, many centuries, and then you can every century pick out a January 1st. So you have 96 different January 1sts from a different year. So that's kind of yeah, I mean, that's one strategy for initializing your ensemble. And then as you do your data simulation experiments, they all start to get pushed to real world observations. And then the final ensemble that is now a good representation of a particular year, you use that as initial conditions for following experiments.
Okay, thank you.
Yeah.
Can I ask you a question on the next slide, Vassili?
Yeah.
Yep, cool. So I don't understand the physics very well, but if I look at your K equation there, if I squint at that, it kind of looks like a sort of least squares or a Galerkin projection that's been damped by a factor R. So R denotes some sort of residual error, and then you damp your correction in accordance with how big that residual is?
Yeah, so R is prescribed. So, and R is, sorry, I didn't mention this, but R is different for every observational type. So every satellite has its own error bars. All Argo floats have different error bars.
Oh, okay. So, and it is a measure of the error or the estimated error then, I guess, yes?
Yeah, that's right. Yeah, it's not only instrumentation error, it's also representation error. Because you can't perfectly observe the model the same way that a satellite observes the sea surface temperature. So yeah, this R kind of incorporates the instrumentation error and also how well or not we can observe the model the same way that the satellite observes the Earth.
Cool.
Yeah.
Thanks.
Cool. All right, so maybe I'll go on, I guess, unless there's no other questions. So now kind of getting into the results. So all of these data simulation experiments, estimating the state and the parameters, were undertaken during the period from January 2010 to December 2011. The reason we picked this period is that it's only in the late 2000s that the ocean starts to become well observed. So what I mean by that, we have more and more instruments observing different parts of the ocean. And then at the end of this, I needed to be able to test how well the learned parameters did in an out of sample setting. So I needed some time from the end of this experiment to the end of the observed record. So during this 2-year period, in these experiments, these initial ones, the state was corrected and the parameters estimated every 28 days. And what you see in this table is globally averaged mean bias. So the difference between the observation and the model averaged over the entire globe, and also the mean absolute deviation. That's kind of a more robust measure of error. This gets away from the fact of having positive and negative biases cancelling each other out. So these errors were calculated over the second year of these data simulation experiments to kind of remove any spin-up transient behavior. And all of the errors are evaluated prior to the analysis step. So they're true error measurements. I might just hop back to this Kalman filtering diagram. So what I mean by that, errors are evaluated at this point here, not this point here. They're evaluated before we've made a correction due to the observation. So it's a fair estimate of error. Okay, so you can see in bold, so this is the baseline case, the mean absolute deviation and bias, the sea ice concentration, under sea ice temperature, sea surface temperature, and in situ temperatures. This is temperature at various depths within the ocean. All of them pretty much demonstrate improvements upon the baseline, which you would hope, other than a couple of, sea surface temperature bias with albedo, but it's, again, this is due to biases, positive and negative biases cancelling each other out. In bold are the ones that have the least bias or least mean absolute deviation. So the problem is when you're assessing these cases on purely the data assimilation statistics is it's impossible to tear apart the contribution of state estimation to parameter estimation, because the observations themselves are doing so much work and pushing the model back to where it should be. It's hard to say what the relative contribution is to the arguably improved parameters. So the only way to do that is an out of sample test of the model running without data assimilation, which I'll show in the following slides. But before we do that, I thought I'd just show you what these parameters actually look like. So for each of the experiments that were quantified on the previous slide, none of the parameters seem to have any strong temporal dependence. So what I'm showing you here is the globally averaged shortwave length scale as a function of data assimilation time. So each dot represents, the distance between each dot is 28 days. So the red line is estimating only shortwave radiation. So you can see there's some transient period, and then it kind of plateaus to 20 odd meters. When you're additionally estimating shortwave radiation, length scale, and albedo together, it converges to a shallower shortwave length scale. And as a reference, this black line is what is done as standard in the baseline model. For ocean albedo, again, the black line is the globally averaged baseline case. And here, these are the values that are estimated as a result of the Kalman filter. The blue line is estimating albedo only, and the green line is estimating shortwave and albedo together. So what the converged maps look like, if you like. So this is estimating shortwave only, the final converged estimated map. So that's associated with this dot here, if you like. We're having, so green means longer shortwave depths. So the heat can be distributed to deeper parts of the ocean, and purple is shallower. So in purple, we're concentrating the heat near the surface. Green, we're distributing it to greater depths. This is the albedo map, and we're estimating albedo only. Purple is less reflection, green is more reflection. And these two cases are the shortwave and albedo when you're estimating these two things together. So you notice that So you'll notice they're similar, but there are some interesting differences. So here, when we're estimating shortwave only, we have this patch of green here in the Pacific where we're trying to get heat away from the surface. There's a warm temperature bias here in the model as standard. So we're trying to get rid of that heat. And if we're only estimating the shortwave length scale, the only way to do that is to send the heat to greater depths in the ocean. So increase this length scale. But you'll notice when we do this in a joint fashion, when we're estimating it in conjunction with albedo, there's less of this signature of having a deeper shortwave length scale, because we can rely on albedo to do some of this work for us. So albedo is reflecting some of this heat before it even gets into the ocean. Okay, so as I mentioned before, it's all well and good to estimate these in a data simulation context, but the observations themselves are doing a lot of work for you. So the only way to assess how much, if at all, that these parameters have improved the model is to run these in an out-of-sample multi-year context. So we took the full ensemble at the final day of the data simulation run, ran them all off as individual simulations for 8 years. The black line is the globally averaged sea surface temperature bias in the standard model. The red line is the case when we've only estimated the shortwave length scale. So in the red line, we're using the shortwave map and we're using the standard albedo map. So the red one is the only one that actually improved the model bias. Either of the other cases that used albedo actually produced a worse model. So this is kind of an important point, that data simulation statistics alone are not capable of telling us the relative contributions of having better parameters, better or worse parameters, and the influence of updating the state. So you might think, oh, well, that's not such a great big improvement in bias. But this is due to positive and negative biases cancelling each other out. When we separate that into the contribution of positive bias and negative bias, you can see there's a persistent improvement in the shortwave only case for positive bias. And we've also reduced negative bias in the Southern Hemisphere summer. So what the bias actually looks like. So this is the bias of the standard model. So this is HADI SST. This is an observational product, observational data set. So the observations minus our baseline experiment indicate that the baseline is larger than the observations in this region here. And this is a typical warm bias in the Southern Ocean. And the model is cooler almost everywhere else. And you can see from these other maps, so this is the baseline case minus our shortwave estimated one. So what you want to see here, ideally, is where it's green here, so where the baseline model is too hot, you want the estimated case to be cooling it, which is what you're seeing. Where you see green here, you want to see purple here. Where you see purple here, you want to see green here. So only the case when you're only estimating shortwave are all of the changes in bias going in the right direction. When you're estimating shortwave in conjunction with albedo or albedo only, you're not getting an improvement, and it's in fact going in the wrong direction. Incidentally, these lines that you're seeing on the graphs, on the plots, they indicate regions that are statistically not different from the baseline case. So anywhere where there's color, it's a statistically significant difference from the baseline case. So that's sea surface temperature. So it goes to, logically you would think, well, if I'm getting sea surface temperatures better, then I would presumably be getting sea ice concentrations better. So typically we have this problem in the Southern Hemisphere where we don't have enough sea ice because the ocean's too hot and it melts too quickly. So this is the bias in sea ice between another type of observation and our baseline case. So you can see we've got not enough sea ice in our model in the Southern Hemisphere because it's too hot down there. But in our baseline scenario, we are adding in additional sea ice where we need to, and we're taking it away where we need to. Again, that's the only scenario in which the biases are going in the change in bias is going in the right direction. And finally, in terms of the atmosphere, some of you might not be familiar with this quantity. It's referred to as H500, essentially the height of the 500 hectopascal isobar. So strong gradients in this field are an indication of where the jet stream is on each hemisphere. And due to thermal imbalance, that's a relationship between meridional gradients in surface temperature and vertical shear in the atmosphere. If you're getting the sea surface temperatures better, then you would also expect to be getting the location of these jets better. Hence, you would be expected to have a less biased H500 field, which is what we see. And again, consistent with the previous quantities, it's only this case where we're estimating only shortwave that the biases are being changed in the right direction. So to put all that in a table, integrating those fields, if you like, over the entire globe, only for positive biases or negative biases, sea ice concentrations globally, Northern Hemisphere or Southern Hemisphere in isolation, and H500 either globally or only positive biases or only negative biases. The shortwave only case wins hands down. So clearly, albedo is an inappropriate parameter to be addressing these biases. So as I mentioned earlier as well, the sensitivity to data simulation cycle length is also really important. So here we've looked at the sensitivity of how these parameter maps themselves change as you change your cycle length. So again, as a reference, this black line is our globally average shortwave penetration depth that's used in the baseline case. All of these experiments start from the same ensemble of parameters, but depending on how often you do the assimilation, they all converge to different parameter maps, which is kind of interesting. So this graph over here is essentially taking the final point of each of these experiments and showing that they kind of plateau as you get out to longer and longer data simulation cycle lengths. And again, they all qualitatively look similar. But not only is the globally average value decreasing, but they're pretty much decreasing systematically everywhere, other than here in the Arctic. So then to properly assess these maps, we need to go through the same exercise of running them all as multi-year climate forecasts. So I won't go through all of the same sea ice concentration, SST and H500 diagrams. I'll just kind of summarize it all in a table. In general, longer DA cycles produce less biased models, but in selecting a DA cycle length, you are saying something about the biases that you find important. So you're essentially estimating a parameter map or sets of parameters that are minimizing biases over the timescale of interest. So which is why the 3-day cycle length actually outperforms in the negative SST bias, which is in the Southern Ocean. And this is related to the sea ice concentration bias in the Southern Ocean as well. And these biases, because the sea ice melts so quickly in the model, these biases are imprint upon the system over shorter timescales. Hence why you would expect a shorter cycle length to do better at these particular biases. But given that, holistically, we're still going to select the 28-day cycle length as being arguably the best representation of reality that we've got. So to maybe just delve a little bit into the physics and see, outside of comparing it to observations, how has this actually changed the structure of the ocean? In the 28-day cycle length, where again, we're only estimating the shortwave length scale, the mixed layer depth of the ocean, it's seasonal. It's seasonal as standard. So in winter, you have larger mixed layer depths due to sea ice formation. So when sea ice forms, the water surrounding the sea ice becomes more salty because the sea ice is extracting predominantly fresh water. So that salty water becomes more dense, and hence the mixed layer depth increases. So this is why you have these kind of big green patches of larger mixed layer depths in the Northern Hemisphere winter here, and the Southern Hemisphere cooler months here. So this is the estimated case. So when we take the seasonally averaged mixed layer depths of the estimated case away from the baseline case, we get these maps that look very, very much like the parameters that we prescribed. So mixed layer depth in the model is shallower where the parameters are smaller, and it's deeper where the parameters are larger. What is interesting though, the parameters themselves are time independent. So the parameters don't change with time, but the influence upon the model does change with time due to the seasonality. So it's more than just a simple bias correction. The parameters are changing the behavior of the model. Okay, so all well and good. We've statistically shown that we can produce a better model, but the parameters themselves, the parameter maps themselves, do not resemble the observed albedo of the ocean, nor do they resemble the observed opacity in the ocean. In and of itself, it's not necessarily a problem. This is typical in turbulence modeling, where if you think of it, the eddy viscosity bears no resemblance to the kinematic viscosity of the fluid. And eddy viscosity is actually a property of the Navier-Stokes equations at finite resolution. And for certain scales, eddy viscosity has been shown to even be negative for certain scales, and we've previously shown this in atmospheric, oceanic, and also turbulent channel flows. However, there are many parameters in coupled GCMs, and I'm not presuming that the two that we've looked at today are the optimal selection. If you think about it, the one that worked was the shortwave length scale, and this modifies the source term of the internal energy equation. This is kind of getting back to why I was showing the equations in the beginning of the talk. And this internal energy equation includes biases and shortwave distribution, but also biases and turbulent mixing. And the Kalman filter itself cannot differentiate between the sources of bias. All it sees is a difference between the observation and the resulting field from the model. So these estimated shortwave maps could well be addressing insufficient mixing in the ocean as opposed to inappropriate representation of shortwave radiation. So just to kind of wrap things up, shown this ensemble transform Kalman filter has been used to estimate spatio-temporally varying parameter maps of ocean albedo and ocean shortwave e-folding length scale on the basis of 28-day forecasts. The estimated parameter maps in these data simulation experiments resemble known biases as opposed to physically observed properties. And in an in-sample sense, all of the combinations improved the coupled GCM. However, in an out-of-sample sense, when you're running multi-year forecasts, it was only the shortwave length scale on its own that systematically improved the model. So to our knowledge, it's the first time such an undertaking has been achieved in GCMs of this size and complexity. And whilst the parameter maps may appear aphysical, there is a precedent for physical parameters in solar turbulence modeling. But in future research, we'll try to get a better physical understanding of how these parameters have modified the underlying model, and then potentially look at estimating turbulence parameters instead. Yeah, that's it. Thank you.
Thanks, Vassili. That was a really interesting talk. Does anyone have any questions for Vassili? While other people are gathering their thoughts, just with regards to your short wavelength correction and the mixed layer depth.
Oh, yeah. Sorry.
Have you thought at all about what this would mean for El Nino? Like, I know you probably you don't necessarily have the resources to do sort of decadal scale runs with these sort of things and look at the El Nino statistics, but do you have any sort of thoughts on what this would mean in terms of the depth and the frequency of El Nino?
Well, so you're right. To get a proper estimate, if we've improved El Nino forecasting, one forecast isn't sufficient. You need to do forecasts from multiple start dates. So whilst I can't definitively say it's better, because we haven't run the cases, we have shown that SST bias has been, sufficiently reduced in those regions. So I think that's a positive sign. And in situ temperature has also been reduced, and that's to do with thermocline depth. So I guess it's promising, but I can't say yay or nay.
Yeah, sure. That's a difficult question.
Thank you.
Anyone else got any questions for Vassili? Lots of positive comments.
Okay, great.
There are hands up. If you look at the hands.
Oh yeah, sorry. Tushari, I'm assuming you don't have a question. That's a legacy hand, I believe. Murali, do you have a question?
Yes, I do. Hi, Vas.
Oh, hi, how you going?
Good. Can you go to that slide where you explain the common gain matrix?
Yep. This one or before?
Yeah, this one.
Yeah.
So you did mention that you preset the value R. Is that correct?
Yeah. So R it's different for every observation type. So a satellite has a different R than a float in the ocean. Yeah, that's right.
Okay.
And that's to do with it's to do with instrumentation error of the instrument. But also how well we can mimic the way that hardware observes the world.
Okay.
So it's representation error and instrumentation error together.
So it takes into both. It takes into account both. Okay.
Yeah.
All right. Thanks.
I don't know if you can see in the group chat, Vassili, but Kabir has a kind of related question, perhaps.
Okay. Let me maybe. I'm sharing my screen.
Would you like to ask your question,
Yeah.
Kabir?
Yeah, I could just speak to the question directly. So thanks for the nice presentation, Vassili.
Oh, great, thank you.
Yeah, so the question is, if you could please comment on the effect of overall on the representation of the observation in the data assimilation output. How does the overall on the estimation of the observation error, how does it affect the assimilation outputs?
So I guess you're referring to the specification of R. How sensitive are the results to the specification of R? Yeah, so there is,
Exactly.
so there is a tuning exercise that you kind of need to go through. Maybe I'll go back, perhaps best illustrated in this diagram here. Every time that you're doing a simulation, this is kind of what I was talking about, these PDFs. You see how the PDFs get skinnier because all of the Earths are looking more and more similar. You need, one thing that you kind of need to be wary against is all of these Earths becoming too similar. And one way that you can control for that is through this R, to make sure that there's always continual, you're not pushing too closely toward the observation. Because I mentioned the limiting case where when all the Earths become the same and there's no standard deviation, there's no error covariance, the Kalman filter interprets that as being a perfect model, which it's clearly not. So R, so R, it is kind of like a tunable parameter, and you need to maybe put it this way: the floor of R is the representation error and the instrumentation error of the observation, but you need to you can also increase R to ensure that you have a healthy data assimilation system.
Yeah. So in a situation when the actual R is unknown somehow or could be difficult to estimate, so would it be preferable to make a bigger R to start with, or to start with a smaller R?
I think you kind of usually start with a larger R just to ensure that you don't have ensemble collapse, so all of your Earths becoming the same. And then you can start to run sensitivity experiments with different values of R, which is kind of what we did in the kind of original Sandry paper. I guess you're always trying to improve the fit of your model to the observations. So there is a quantitative way that you can estimate how, you can qualitatively determine if things are getting better with your changes to R or any other parameter. So in terms of like bias and mean absolute deviation, everything, all your decisions are really based around how well the forecast of the system is matching observations. So to answer your question, it can be sensitive to it, but there is a way that you can intelligently select these parameters.
Yeah, thanks for that. Yeah, that's really helpful. Yeah, thanks for that.
Great, cheers.
Did anyone else have any questions for Vassili? Rena, yes?
Yes, I just have a question in the Kalman filter slide. Just go back on slide, Vassili, please.
This one or back the other way?
I don't know, it's just maybe I missed that one, but could you please say the meaning, like what is the physical application of Y here? Is it like
Y? Yes. Yeah. So sorry, the definition of Y was on the first slide. Y is the observation.
Okay.
So Y is your satellite measurement or your hot wire measurement in a wind tunnel or whatever your application is. There is actually nothing physical about the Kalman filter. This has no knowledge of the fluid mechanics. It was developed in robotics, really, and position control. So, yeah. So does that answer your question? Yeah. So Y is the real world observation.
Okay. Yeah. Thank you.
Yeah. No worries.
Any other questions for Vassili? So there are some nice comments in the text box. So thanks everyone for participating. And yep, I would second those comments. That was a really interesting talk. So yeah, thanks again for Vassili for presenting with us with such a great talk.
My pleasure. Thank you. Thanks for the opportunity to talk to everyone. Thanks everyone for their time as well.
Great. All right. Thanks everyone. We hope to see you all next Wednesday. And yeah, goodbye.
Great. See ya. Bye.
Bye.